Okay, welcome back. In the last video we have calculated all the direction cosines for this truss element. We have 4 elements here, 1 2 3 and 4. For all the 4 elements we have calculated the direction cosines L1 M1, L2 M2 for element 2, L3 M3 for element 3 and L4 M4 for element 4. Okay, now you see for these 4 elements how many nodes are there. For element 1 node is 1 and node 2, and for element 2 nodes are 2 and 3. For element 3 nodes are 3 and 1, and for element 4 3 and 4. Okay, so what is it? How many nodal displacements are there? It is a 2-dimensional problem, so in each node there are 2 displacement in x direction and displacement in y direction. What is the displacement in the node 1? Q1 and Q2. Q1 it is the displacement in the x direction, Q2 displacement in the y direction. Similarly Q3 and Q4 for the node 2, Q5 Q6 for node 3 and Q7 Q8 for the node 4. Q7 Q8, Q7 it is the displacement in the x direction, Q8 it is displacement in the y direction. Okay, let us find nodal displacements. Before that, to find the nodal displacement, we know that KQ is equal to F, where K is the stiffness matrix, Q is the nodal displacement and F is the force vectors. Okay, to find the nodal displacement, first we need to find stiffness matrix. We already know what is the stiffness matrix for the truss element. This equation 4x4 matrix, it is the stiffness matrix for one element. Okay. Okay, in this problem there are 4 elements. This is the stiffness matrix for the truss element. For the first element we are using L1 M1. For the second element L2 M2. Third element L3 M3. Similarly for the fourth element we are using the direction cosines L4 and M4. Okay, let us find what is the stiffness matrix of the element 1. To find the stiffness matrix we need area, Young's modulus, length of the element and L and M. L and M are the direction cosines. L and M it is already calculated for the element 1, element 2, 3 and 4. L and M, L1, M1 it is 1 and 0. Okay, what is given the area? Area it is same for all the elements and Young's modulus is also same for all the elements. A is 100 mm square, E is 2 into 10 raised to 5 Newton per millimeter square. Okay, A is 100 mm square, E is 2 into 10 raised to 5 Newton per millimeter square, divided by LE. LE means length of the element. What is the length of the element 1? It is 40 mm. AE by L. See here, L square. What is L value here for the element 1? L value, direction cosine, it is 1. M is 0. L is 1 and M is 0 for element 1. Similarly, L square it is 1 square, 1 square it is 1. M is 0, L is 1, 0. Again it is L value is 1. So, L square is 1. So, it is into minus 1. So, minus M value is 0. So, 0 into any value it is 0. Similarly, you will get all these values for the given direction cosines. You take 10 raised to 5 outside. If you take 10 raised to 5 outside for one stiffness matrix, you have to take the same value for all the stiffness matrix of all elements. How you got this 5? This 1, minus 1, 1, 10 raised to 5, it is only 10 raised to 5 is taken outside. So this 100 into 2 divided by 40, this value is 5. 5 is multiplied to all the elements. So this is the stiffness matrix for element 1. What is this 1, 2, 3, 4? 1, 2, 3, 4 are the degrees of freedom for the element 1. See here. For node 1, displacements are 1 and 2, Q1, Q2. For node 2, it is Q3, Q4. So 1, 2, 3, 4. So 1, 2, 3, 4, 1, 2, 3, 4 is written here. Okay, similarly, K2. K2 is calculated here. 10 raised to 5 is outside and remaining all the elements are multiplied with this 0.66. Similarly, for element 3, where the direction coefficients are minus 0.8 and m3 is minus 0.6, how this got? You see here, for element 3, L3 is x1 minus x3 divided by Le. By this, it is minus 0.8, m3 is minus 0.6. Similarly, for element 4, okay, already direction coefficients for all the elements is calculated. Just you need to substitute the values in the stiffness matrix equations. So, similarly, K3 is calculated here. K3. What is 5, 6, 1, 2 here? Why it is 5, 6, 1, 2? Okay, let us see here. It is stiffness matrix for the element 3. This is the element 3. We already discussed what are the initial node and final node. To continue this direction, we have considered this is the initial node and this is the final node. See the direction. So this is the initial node, this is the final node. So Q1, Q2, Q3, Q4, Q5, Q6. Okay, it is Q5, Q6, 5, 6. It is the initial node. Final node is, what are the nodes of the, what are the degrees of freedom of the node 1? It is 1, 2. So 5, 6, 1, 2. Where it is written 5, 6, 1, 2. Okay, similarly 5, 6, 7, 8. It is for the stiffness matrix of the element 4. Now we have got all the 4 stiffness matrix for the 4 elements. Let us add all these stiffness matrix. As in this problem we have got 4 nodes. In each node there are 2 degrees of freedom. 4 into 2, the size of the stiffness matrix, global stiffness matrix, is 8 by 8. In the global stiffness matrix, the size of the stiffness matrix is 8 by 8. You can see here what is written on the top. It is 1, 2, 3, 4 up to 8. It is nothing but the degrees of freedom. Okay, let us consider the stiffness matrix for the element 1. Element 1, what is the size of the stiffness matrix? It is 4 by 4. You already know what is this 1, 2, 3, 4. These are the degrees of freedom. 1, 2, 3, 4, 1, 2, 3, 4. Okay, you have to place all these elements in the global stiffness matrix in such a way that this is the first row. This 5 should be placed in such a way that it is first row, first column, and this element, it should take first row and second column. In this similar fashion, you substitute all these values. Same thing here for element 2. Element 2, degrees of freedom are 3, 4, 5, 6. For example, if you take this 0.66, what is the position of this 0.6? This is 4th row and 4th column. Okay, similarly you substitute all the elements in the global stiffness matrix. For example, if you take this 1.92, it will occupy 6th row, 5th column, and this 2.56, it will take first row and first column. Okay, substituting all the values, this is the global stiffness matrix. Okay, these are the force vectors. Force in the node 1 in x direction, force in the node 1 in the y direction. Similarly, force in the node 2 in the x direction, in the y direction. Force in the node 3 in the x direction, y direction. This is the force vectors. Already we know the equilibrium equation, kq is equal to f, where k is the global stiffness matrix, q is the nodal displacement vector, and force is, and f is the force vector. Okay, we'll continue this in the next video session.